So the daily problem is another tree problem. Number of nodes in the subtree with the same label. You can pause to read it. The idea is that we're given a tree and each node has a label in this string labels. And we want to count up the number for each given node, the number of labels at that node or below. So for 0, there's this A, and then node 2 has an A. So answer at 0, this array we're going to return at 0 is going to be 2. And then for everything else, for example, this node 2, there's this A, and we can't look at 0 anymore. So now it's just E and D. There's only one instance of A there. So we return 1. So it's going to be 2, and then everything else is 1. I'm going to outline just a quick and dirty approach, and then I'm going to optimize it a bit. So the quick and dirty approach, I'm going to use a recursive depth first search. And I'm going to more pivot it. It was my first instinct was to just get a solution down that's the same O of n complexity, big O notation. I'm not going to worry that much about the fluff or anything. I'm just going to have it be quick and concise. And that's sort of more of maybe a competitive coding way to do it. So I'm going to use a default dict for the adjacency list, where we can see we're given this list of lists edges. So it's more akin to a graph problem than a tree problem where we're given a root node or anything like that. So first thing we want to do is turn that into an adjacency list. So I'll say ADJ, a lot of people say graph here, but I'll say ADJ equals default dict list for u, v in edges, ADJ at u dot append v, and vice versa. Okay, we have that, and then I'll say answer equals 0 times n. Ideally, I would say none times n, but if I want to just return this right now, if this was none times n, it would throw an error because it wouldn't be the right format of data. So that's what I'm going to want in the end, and then I'm going to have something like define the depth first search, and then I'm going to say node, the current node, and the parent, the previous node. And the reason why I want to pass the parent into this depth first search is, let's say we're looking at 0, and then we look at a depth first search at 1. All 1 sees from this adjacency list is I'm connected to 4, 5, and 0. It doesn't really know anything else, but we want to designate, well, don't look back at 0. Look at 4 and 5. So we're going to pass the parent and just say at some point, look through all the things that are connected and ignore the parent. This is a point to point out. They tell us that the root of the tree is 0. But the root of the tree, if they didn't say that, could just be anything. We could say 6 is the root of the tree, and 2 is its only child, and then 3 and 0 are that child, and so on. The conceit of the problem sort of requires that we designate a root before asking this question. But there are a number of tree problems where you can just choose any node. That's probably what I would do if they didn't explicitly give us a root that they want us to use anyway. So anyway, in the depth first search, my initial strategy that isn't very quick but is pretty concise and intuitive is to use a counter. And what a counter is a dictionary specifically meant to keep track of the number of elements in a collection. So if we say something like, let's just say for now, we'll say something like that, just as a test example, and then let's say counter equals counter of labels. So we're creating a counter based off of this string, A, B, A, E, D, C, D. And then we'll just print counter and show what that prints. So what that's going to print is, look, there's 2 A's in that, and there's 2 D's, and there's 1 of everything else. And the reason why I'm using counters is not only because this is like useful for what we're doing conceptually, but also because unlike dictionaries, you can say something like counter plus equals another counter. And let's have this other counter, let's just say counter labels again. And now when we print it, we're going to see, oh, A has 4, D has 4. We've doubled each instance because it's smart enough to know, add each element together, add the number of instances in each element together, because that's what a counter is meant for. With a dictionary, if you said dictionary plus equals another dictionary, it doesn't know what that means. There's not any built-in way to add dictionaries because they semantically aren't really intended for that kind of purpose of recording frequencies. I could also say counter plus equals counter based off of a dictionary that has a comma 10. Let's say G is 10 as well. Oops, I want these to be strings. And then we can see it successfully added in the existing element A, and it also added in this new element G. So with that in mind, the basic idea is for every single instance we create a counter, we add we're going to return this counter in the end, which isn't going to be useful when we call the depth first search in the overall function. It's going to have a void aspect too, where we're altering answer at each instance. But we're going to return this counter up to the previous recursion of this depth first search call, up to be added to the previous function's counter. So for example, let's look at this B. We're going to create a counter with 1 in it. So we'll say something like counter from labels at node. So then there's this single B in node 1's depth first search call. And then we're going to call depth first search and add each return from each depth first search at each child to this counter. Then we'll say for child in ADJ at node. And then we want to say if child is parent. So for example, from this one, if we're looking at the 0, continue. And then we want to say counter plus equals depth first search at child, and then the new parent for that call is the current node. And then the final thing we want to do is say answer at node equals counter at labels at node. And we can see that's what we initialize this counter to is labels at node. And then presumably, if we initialize this, it's going to say that, well, we have 1A. And then in the end, after this loop, it's going to say we have 1A, 1E, and 1D. And then it's going to say, well, how many A's do we have in that? 1. So return that. And we can kind of see there that we'll always return at least 1 for every single node's number of similar labels, which makes sense because you always have yourself. You always have your own node's label. So this runs, it works. To me, it's pretty intuitive, but we can definitely optimize it a bit because it's kind of middle of the road. The first thing we can do is take away this default dict and just make it a list of lists. There's a point where you'd want to use a default dict if your key was not an integer, but here it is an integer. So we can say for blank in range n. And this just works exactly the same, but with a little bit less fluff because default dict presumably has a bunch of methods that we don't need. Same with counter, we don't really need that. In fact, creating all of these counters, this is O of n space and time complexity. It's O of n time complexity because you're performing operations for every node, and not any more than that and not any less than that. So it's O of n. The space, even though you're creating this new collection, this new counter for every single node, you know that for every node when you create it, it only has one element, and then you're just combining them together. And the largest instance is going to be the root node that has n elements in its counter. So it's still O of n space complexity, but it is inefficient to have to create a new data structure for every single recursion of this function. So instead what we can do is just have the counter outside of the loop. And the idea is to say, let's take this 2. It's true that this 2 is what we want to look at is this node and its subtree. But also what we could say is, what we also could look at is the entire tree minus everything we don't want to look at, which seems a little more convoluted logically, but it's useful because we can kind of take this rolling sum. And you see this a lot in like array problems where you take a prefix sum or a rolling sum and you're subtracting different things to get a range or some sort of difference in sums. Here we can do that too, but in a tree structure. So we'll say counter equals 0 times, and I'm going to change this to none right now before I forget, 0 times 26. And again, we're not going to use a counter because that has fluff that we're not going to use anymore, such as the capacity to add counters together. We don't need that. So we're just going to use a list. And this is going to be index 0 represents the number of A's, index 1 represents the number of B's, and so on. And that's the first thing we want to do, is translate the character A to the number 0. So what we're going to do is we're going to have, well, first off, if we wanted the character, we would just say labels at node. And then we want to translate this into a number, so we're going to use the ord function, which then says what's the rank of that character. Character A, let's say we're looking at character A, ord of A is going to be 97, ord of percentage sign is 105 or whatever. It's not that, that's going to be a lowercase character, but A is 97, B is 98, and so on. So we can just say minus 97 to offset that. And now A is 0, B is 1, and so on. So once we have that, we're going to say, the first thing we're going to do is, let's say we reach a node like this 2. We want to take a snapshot of the current number of A's in the entire tree before we've iterated through this subtree. So everything we don't want to look at. So I'll call this above, because it's sort of all the A's above this 2. So we'll say above equals counter at bar. And in the end, what we're going to do is then we're going to iterate through this subtree, and we're going to say, now at this point in the code, at this line, counter is different than it used to be, because we're going to change it. And now counter includes everything in the tree. And then what we want to do is say answer at node is going to be equal to counter at bar minus above. So we're saying counter at var now, at this point in the code, after we've written out something here, represents all of the A's in the tree, and then we want to subtract the A's that we don't want. Anyway, so let's include all the A's in this subtree. So then we say for, well, the first thing we want to do is actually just say counter at var plus equals 1, because we have the node itself that we're looking at. And we can see again, answer at node. If let's say it was a leaf node and had nothing else, like this 6 here, we'd say, okay, above is everything else, and now add 1 to that. So if there's no child nodes or anything, we're at least going to get 1, which again logically checks out with the intuition around this problem. So we want to say for child in ADJ at node, if child is parent, continue. And then we just want to say depth first search child node. And this is pretty much the same logic, but we're not recreating a bajillion counters. We're just keeping track of 1. And that turns out to be a significant optimization. Straight up. And if we look at previous examples, that's not the first 100% I got too on that type of optimization. So that's that problem. I mean, cool to get 100%, but optimizing like this doesn't matter. You're not really changing the big O notation. And this might just be a weird anomaly, so who knows. But that's 2 ways to do this problem.